going to be a gentle introduction, which is good for me, who doesn't know a lot about chips and integrated circuits, to place and route algorithms for digitally integrated circuits. The focus is going to be algorithms for global placement and also globally used routing algorithms for how to place circuits on in the integrated circuits. Thomas got his interest in the subject from the electronics corner of the local recycling center, where he was trying to find out how to build digitally integrated circuits and understanding how proprietary software used to create the chips and circuits work. And since there was not any lectures on this at his university, he tried to figure it out himself. So please come in, find a seat. If you see somebody looking for a seat, put up your hand to indicate where the seats are. And then, most importantly, for the next 30 seconds or so, give a warm round of applause for Thomas.
Thank you for the introduction. Good morning, everyone. As said, I will talk about place and route algorithms that are used for digital integrated circuits on silicon. So, what is that? I'm sure you've seen those, and maybe some of you have wondered what's inside. I wondered very often, and when you don't really have much of special equipment, you can still have a look at what's inside, and there's a really brutal method how to do it. You take your blowtorch, you heat this epoxy case, and eventually the epoxy thing will crumble away, make some ugly fumes, so don't do it inside. And if you have a cheap microscope, you can see something like this. So that's actually the silicon chip. It's much smaller than the package. It's only a couple millimeters. And what you see on this is there's diversity, lots of different circuits, and the thing marked in green is what is supposed to be a digital circuit. I don't really know for sure for this one. And this is exactly the thing that I want to talk about today, or how to create it. So I will focus on place and route algorithms. That's somehow part of what I would call a type of compiler for silicon circuits. And I will focus on how this compiler works, and I will not tell you today how to use it. That's somehow another topic. Most of chips are proprietary. That's no big news. I heard people saying that we know that there's Intel inside, but what is inside Intel? We don't know so well. There's lots of obscurity in proprietary chips. There's sometimes missing documentation, incomplete documentation. We rely on proprietary firmware because we don't have the full documentation. Then we can ask ourselves, do we have, for instance, this for freedoms that we use from free software? Do we have this for chips? Can we use the chips for whatever we want? Can we study them? Probably not so well. Can we share them to some limited extent? Can we improve them? Probably not. It's really difficult because we don't know how they work in there. So can we create open source chips which are completely open, like down to the layout, down to this geometrical representation who tells the factory how to produce them? Answer is yes, we can do it, but there's certain stones in our way. People who do digital circuits usually cannot really get around certain types of software, the EDA software, electronic design automation. And there's roughly 3 vendors worldwide which have some sort of monopoly on this software. And they set rules. When you want to use this software, you have to sometimes sign NDAs, there's restrictive license agreements. And they basically don't allow you to publish the output of this software. It's a bit like you would write a text in Microsoft Word, and you would not be allowed to publish the text because it could somehow leak information about how grammar correction works. Then there's another difficulty that's related to the factories, to the fabs who create the chips. There's usually NDAs involved because you need to get access to information, what they can produce, how you have to design your chip that they can correctly produce it. And this blocks you from publishing, for instance, the layout of your chip. Now, it would be great to have some free and open source toolchain to create those chips. It would help a lot. It would also help us, for instance, to try new ideas, because we could modify and extend this toolchain. We cannot do this with commercial software. It's also much more accessible, because the software of these major 3 vendors, it's hard to get. So if you're a small entity, it's probably difficult to even get access. And free and open source toolchain would also be really helpful for education, because you could actually show students how things work inside. So why do we care now about this? So recently there were many things happening in the field. For example, started with a US foundry called Skywarder. They opened their process design kit. So they published this information that you need to create a chip with them. They published it open source, and that's one of the first foundries that did that attracted lots of interest. There was soon Google and DARPA on the project. Then there is a project in the US called the Open Road Project. It's basically a free software place and route toolchain. Then recently there was a German fab doing something similar. They started opening their process design kit. So this allows basically everybody to have a look at it and create chips for this foundry. Then the European Union is drafting the CHIPS Act. That's another big topic probably would be worth a full talk itself. Then, that's somewhat my personal opinion, but I have the feeling that tech vendors get more and more restrictive. It's harder to understand the technology. So I think it would be time to have alternatives. So let's have a look at how people usually do digital circuits. You often start from a high-level description in a hardware description language. That's kind of your source code. And you want to turn this into a chip in the end. And for that, you need a foundry who produces the chip. The foundry wants from you a layout. That's basically a vector graphic representation of your circuit. They also want money. And they give to you the design rules. So basically, they tell you what kind of structures they can fabricate. For instance, how tiny the transistors can be, how thick the wires need to be. And when you have these design rules, you can create standard cells, a so-called cell library. That's a collection of logic gates that you can use in your digital circuit. Then, based from that, you can compile your source code into a circuit. That's called logic synthesis. You get a netlist. That's basically like a text representation of a circuit. And now there's a big piece missing. That's the place and route toolchains, which basically take this netlist, they take the information from the foundry, the design rules, they take the standard cells, and they assemble it into a circuit representation that can actually be sent to the factory for fabrication. So a quick recap about digital circuits. They're built from logic gates. They implement small Boolean functions. That's, for instance, inverters, AND gates, OR gates, NAND, XOR, and many more. Here is a picture of how such a gate looks inside schematically. It's built from transistors. Here on the right, for instance, is an inverter. Now, it's not so important for this talk to understand in detail how this works. Just more as a reminder if you've seen it already before. Then we need storage elements that can be, for example, flip-flops. Flip-flops, they sample the input signal when the clock edge arrives, and they transfer it to the output and then hold it there. And once we have those logic gates, we can assemble them to big circuits, like CPUs or whatever. And in practice, this can be really many, like up to millions. And when you do this place and route step, you get vector graphic representation, and when you look at this, it's very hard to understand what it should be. For instance, the picture on the right is maybe 6,000 cells together with wires. When you zoom in, you start seeing a bit more structure. You recognize that things are arranged on rows. You see some patterns that seem to be repeating, and that's this logic cells. In 2 dimensions, it's kind of hard to understand at first glance what it means. So if you look at it in 3 dimensions, it's a bit more intuitive. Here you can see this row-based structure, so these gates are really placed in rows, and in between there's those lines. That's the power stripes, that's part of the power distribution network. Then on top you would add the wires, which connect the gates. They're now not displayed, that you can actually see it on. So maybe you already know silicon chips, they're constructed layer by layer. You start on the lower side with the silicon. That's where you create the transistors by adding doping and polysilicon for the gates. That's not so important for place and route. We kind of try to abstract that. What is much more important is the layers above. That's the metal layers, which you use for electrical connectivity. So that's usually multiple metal layers, and there's via layers in between where you can connect between 2 metal layers. Now what you see here is such a logic gate, a standard cell. It's actually an inverter. That's one of the simplest cells you can build. It's made of 2 transistors. Here on the left you see the schematic representation. In the middle you see the 2D representation. That's usually what chip designers have on their screen. But I find it kind of hard to understand from the first glance what it actually represents. Therefore, here on the right there's also a 3D representation. And you see more or less a one-to-one mapping between the schematic and the layout. For instance, you can see both transistors, you can see the wires, the pins, and the pins is where you connect to the gate in the end. Standard cells can be much larger and more complicated. This, for example, is a flip-flop, 1-bit storage. And for place and route, we like to simplify this a bit. So we don't care so much about the transistors below. What's important for us is the metal layers and the pins, because we need to know where to connect the wires. So let's get to place and route. What we need to do first is we have these thousands or millions of components. We need to decide where to place them on the chip. Then we need to distribute the clock to, for instance, the flip-flops. We will not talk about this today. I will talk about how we then connect displaced cells. Then afterwards, usually people try to verify the timing or try to fix the circuit when timing requirements are not met. I will not talk about this today either. And I will also not talk about verification, which is actually really important because you want to make sure that what you just built is what you wanted. So, placement. You need to find good positions for all the components on the chip. And what does it mean good? Usually we want to optimize certain things. For instance, the wire length, because the wire length will be important for how your circuit performs, how fast you can run the clock. But it's also important for routing. The shorter the wires are, the easier it is to route the circuit. There's certain constraints. For example, the obvious one, the components cannot overlap. And you also want to make sure that the routing is feasible. So you don't want to create situations where you would need to pass too many wires somewhere, which is not possible. It's really useful to break the problem down into multiple steps. And usually what people do is they start with so-called global placement. And this is all about finding approximate locations for the cells. So you can relax the design rules, for example. You say it's fine if some components overlap, as long as the overall density is nicely distributed. And then once you have this, you can go into something that people call legalization. So you try to snap those cells to legal positions. Usually you have a grid. For instance, those are given by the structure of the power grid. You need to snap the cells there. And then you can also do some smaller optimizations, like flipping or rotating the cells in a way that simplifies, for instance, the routing or shortens the wire length. Now, here's an example of such an algorithm for global placement. And the basic idea is we want to place connected components close together. So we imagine that we connect them with springs, mechanical springs, and the springs, they would pull together components which are electrically connected. Now we simulate how those connected cells will move and where they would go. And while we do this, we, for now, completely ignore overlaps. That's fine if those cells, they somehow lie on top of each other. And what this method does is it minimizes the squared wire length. This is where the name quadratic placement comes from. And this type of algorithm is so-called analytic placement. It's mathematically nice because you basically minimize a cost function, and you compute for each of the components how a tiny shift in position will have an effect on the cost function, and you move all the components in a way to decrease the cost function. And that's called gradient descent. The problem with this approach is that it leads to really high overlap, so many cells will lie on top of each other. If you look at an example with a couple thousand cells, you see that there's this black cloud where you have tons of cells on top of each other, and we can't use that. So we need to somehow spread the cells to move away from each other, and the idea is to add another force which repulses the cells. And what you can do is we can actually simulate charged particles which are connected with springs. Because electrical charges, they repulse each other. Those cells will try to not be on top of each other, but go away from each other. And this way we can effectively reduce the overlap. This is an approach used by an algorithm called ePlace, which is widely used in, for instance, this open road toolchain. I think it's also used in industrial toolchains, but we don't really know for sure. So let's have a look at what is the effect of adding this repulsion. Here on the very left, there's a circuit placed with the quadratic placement. You see lots of overlap, it's very dense. Then when we add the repulsive force, we see in the middle how the cells start spreading until on the right they actually reach the density constraints and there's almost no overlap anymore. Once we have this, we can continue connecting the components, and this is done in the routing step. So the goal of routing is to do electrical connections. And we have to do them correctly, so you don't want short circuits, you don't want missing connections. And there's certain constraints. The constraints are basically given from the fabrication process. We have certain types of metal layers that you can use. There's design rules. The design rules, for instance, tell us how close wires can be together or how thick they need to be in order to be properly fabricated. There's some other funny design rules like antenna rules, but I will not talk about those. Often it's good to route special nets separately. So there's certain nets that go to many cells, for instance, ground and the supply network. They basically go to all the cells. That's why we need to make a regular grid. Then another net which goes to many cells is the clock net, goes to all the flip-flops. It's also good to do this in a separate step, and that's called clock tree synthesis. I'll also not talk about this. Speaking in images, what we have before we need to route the circuit is a couple cells which are placed on the chip. We know how they're connected, but we don't yet know where the wires exactly go. That's here shown as these orange lines. And on the right is what we want. We want nice drawn wires which adhere to the design rules. There's an important concept for routing. It's called maze routing. If you know Dijkstra's algorithm for shortest path search or Bellman-Ford algorithm, you know the concept. And the concept is that we move on a graph. We have a source node, destination node. We want to go from the source node, here marked as green, to the destination. We maybe have some obstacles where you cannot go through, like this gray box. And the idea is that we propagate a wavefront from the source, and with each step we remember where we will need to go back to the source. And as soon as we reach the destination, we can trace back and find the shortest path to the source. Now, also the routing problem is good to break it down into multiple steps, and often what people do is they do first global routing, where you find approximate routes, and during this step you can relax the design rules, you can kind of forget about them. And what you try is also to solve congestion, so you try to push signals away from regions which are heavily used. And this way you can then simplify the so-called detail routing, where we draw the final wires, and in this way refine the global routes to actual wires. And in detail routing, we have to respect the design rules, so we need to be aware of this minimum distance that we have to keep not to create short circuits. Now let's look at global routing. So you start with a circuit which is placed on the chip. You know the positions of the cells. You want to find approximate routes. And a good approach is to slice this area into tiles. And now you say that you basically try to find routes that cover the whole tile. So, for example, here you want to find, or you want to connect a cell which is located somewhere here. I have my mouse pointer to a cell which is somewhere here. And you find out that it goes somehow through those tiles, but you don't know and you don't care so much how exactly it will go there. So let's do an example. We want to connect those colorful shapes with each other, and what we know is that between those tiles there is a certain capacity. For example, you can pass at most 2 wires. Then some tiles might be blocked by an obstacle, so you cannot pass any wires, and you have to go around them. One algorithm that's called Pathfinder algorithm, it's also used in FPGAs, has the approach that we just try to route all the nets. Then we try to see if there's problems. For example, if we route those 3 nets, we might end up passing 3 nets through this tile, and the problem is we can only pass 2. And what you can do is we can increase the cost through this tile. So if you're lucky, eventually one signal will decide to go somewhere else, and in this way resolves the congestion. Once we have these global routes, we can use them to steer the path search for the detail routing. So they basically mark a region where the final wires can go through. What you can do once you have the global routes is that you do another refinement step. So for example, you can convert the global routes into thin lines, like skeleton lines, and try to arrange these lines that there's minimal amount of overlap. And these lines, they're already quite close to the actual routes, but there might be gaps, maybe there's still some conflicts. And once you have those lines, you can use them to steer maze routing. So they really narrow down the path search, and you can fill the gaps using maze routing. And if you do this, you end up with final wires. Maybe you have to check for design rule violations. Maybe you somewhere got too close to other wires, and you may have to fix it. If you apply this to a bigger circuit, that's how it looks like. You already seen it. It's hard to somehow really see through what happens there, but that's how it looks. So once this is done, you might still want to make use, for instance, of empty space. What people usually do is they fill empty space with capacitors, and this helps, for instance, to stabilize the power supply. So, if you want to know more about this topic, there's a good book. There's also a conference which is devoted to this topic. It's usually in Paris in summer. I don't know the date yet, but I will be involved in organizing it. It's the Free Silicon Conference, so if you're interested, maybe check it out. As already mentioned, there's the Open Road project, which is a collection of open source tools for place and route, and also some tools for verification of the timing. There is a quite old open source project for place and route. It's called Coriolis. It's developed in Paris at Sorbonne University. I just recently discovered another place and route project. It's called Luna PNR. Sounds really interesting. I don't know much about it, but if you want to have a look at some code and how this is done, might be a good start. Personally, I also work on a project that's called LibreEDA. It's very similar, basically trying to implement place and route algorithms. If you like Rust, that's maybe also fun. Good. So thank you very much for listening. If you have questions, that's the time now. You can also send me a mail later as you want.
But before you start sending emails and reading books and going to conferences, you should line up behind the microphones in the room if you have questions to Thomas. And also on the internet, there is also possibilities of asking questions, and we will read them out, one of the speaker heralds. We already have 3 volunteers for questions over here on the left side for me, the front mic. So could we have the mic put on? And you can ask a question.
Okay. So with this brilliant picture that you have here, and as an example from the previous slides, so it has this couple of island regions. Why they are there? How they are?
Yeah. So how this looks, it really depends on the algorithm you use to decide where to place the cells. And usually you recognize some sort of blobs. And sometimes you can also see it in this big blob, and sometimes also spot like tinier blobs. And this is usually circuits or kind of sub-circuits, which are those cells under each other. They're much more connected among themselves than to the rest.
So is it a result of some external constraint for the algorithm, or is it something that algorithm does it by itself?
No, it's kind of something that just happens if you, like I said, you simulate this network of springs and electric repulsion. And that's something that just pops out, and seems to be some optimum. Yeah.
Fascinating. Thank you.
Thank you very much for the question. Next question in the room, and then we also have a question from the internet.
My question is, you said that when doing global routing, you can ignore the design rules. Can you elaborate on that? Because I actually didn't get that at all.
Yeah, so you can somewhat relax the design rules. So the design rules, they tell you, for instance, what needs to be the minimal distance between two metal shapes. And if you want to respect that, it's actually, you need to do lots of checks. So it's computationally really hard to always make sure that everything works out. And now, the way you relax it is you say, I know how big the wires should be, I know how much distance they should have, and I kind of summarize it in this capacity between two tiles. So from the size of the wire, I can say that, okay, between two tiles, I can have 10 wires at most. And basically, that's how you simplify it. Does it answer your question? In this sense, you don't completely ignore it, but you try to kind of abstract it, and you don't want to make checks for actual design rule violations during global routing.
Yeah, probably got it wrong because maybe you said relax and not ignore.
Yeah, could be.
Good, we have a question from the internet, possibly more, and if you have questions, please line up behind one of the mics. So, Signal Angel, could you please read out the question from the internet?
Yeah, the internet wants to know if parts of PNR done for the FPGAs by the next PNR project, if they are applicable for ASICs or the other way around.
I didn't completely understand the question.
The question is, there is PNR work done with next PNR for FPGAs. If parts of it are applicable also for ASICs or the other way around. So ASIC software being useful for FPGA.
Okay, yeah. I'm not so much into FPGA toolchains, but there's really some differences. For instance, on the FPGA, basically all the components are already placed, and what you can change is the routing. For instance, then I imagine that the placement algorithms, they're somewhat different. I know that for the routing, FPGA toolchains use a similar way to resolve congestion, like this Pathfinder algorithm. So there's some similarity here. If you look at the steps before place and route, like the logic synthesis, I think that there's more overlaps. And I think people already use tools for FPGA design, also for ASICs, like YOSIS for synthesis.
Good, and if any of you sitting down have questions, please don't hesitate to get up and stand behind a mic. We have one more question.
Yeah, so again, this comes from the background of FPGA, from YOSIS and NextPNR. This is what I have used. So these open source alternatives to, let's say, Vivado and all are YOSIS and NextPNR, right? I just want to understand in that context, maybe it also applies to ASIC, is that now I see one of the connected circuit in that green island, and one of the other electrical connection is in the main overlapped region. So what is ultimately the consequence of that? Will I have some timing latency in my circuit in that logical path? What is the, let's say, how do I make sure that if it's not there, it's in part of this main island, how is my circuit better? Will I have reduced timing latency? They will be good? How does I make sure as a layman, how do I understand, okay, placing and routing happened, what happened is a better placement, or let's say it was not that efficient?
So how can I make sure that you don't have time latency? So timing, intuitively you see that long wires might have more like delay. Yeah. That's correct, but often what you try to minimize is, for instance, the quadratic wire length, or like the half perimeter wire length. And now it can be that, so there's also, for instance, there's also other things on the left that we now don't see, like the the pins or pads. And now it could be that actually shifting this whole blob towards there, even though we make those lines a bit longer, still minimizes the wire length because there's more wires going to the other side.
But ultimately, we are trying to minimize the wire length to reduce timing latency. That is what we are trying to do.
Yes and no. Because for timing, it gets more complicated. So tendentially, it's better to have short wires for timing, but not all wires matter the same. So a wire might be on a path where you have like lots of time available, and this wire will not matter much, so you can make it much longer without problem. And then there's other wires which are kind of a critical path where timing is tight and you need to make them much shorter. So you can also make those trade-offs.
Good. It seems like we have a final question, but if any of you want to ask a question, we still have time to answer at least 2 more questions. So please go ahead from the microphone.
Coming from the circuit board designs, they, I think, in layers for a ground plane, voltage plane, and so on. Is there some kind of notion when routing here?
So the planes?
Yeah.
You don't really have planes, but what you do is this grid. So the grid is in some sort your plane, but you make holes in between. Okay. Because you cannot do a plane because, well, maybe you could do it, but people don't do it. I think there's other things that limit yourself because there's some restrictions on density, and you actually want to use also the space for signals. So it's better to have the grid where you can also between pass wires for signals.
Excellent. And we have one more question, at least in the room, and the Signal Angels will have to let me know if we have any more questions from the internet. So please go ahead from the microphone.
So how common or doable is it to do manual optimizations to the placement or even routing?
Manual optimization. I think it's not common at all for digital circuits. I think for analog circuits it's very different. There people do it usually manually. But if you have so many cells, I think it's really hard. Sometimes what I've seen is manual optimizations when you have design rule violations. So maybe your tool chain does something which ends up with some wires getting a bit too close to each other, or some corners of wires being too close to each other, and basically you can fix this manually.
Okay, thank you.
So I think this is all of the questions that we've had both in the room and from the internet. Thomas, is there anything that people haven't asked you that you want to say? Give an answer to?
At the moment, no.
At the moment, no. Good. Well, then everybody please give Thomas a warm round of applause.